Hello guys, welcome back to Structural Geology course. This is our second lecture, sorry, wherein we are dealing with scale. That is to say from microscale to macroscale, or from microscale to to regional scale. So understanding different scales is very important for structural geologists in this field of structural geology, because geological structures and processes operate and manifest across a wide range of scales. All right. So, which is why today we need to understand what is the scale. So, the first question we should ask ourselves is, what is a scale? So, in structural geology, a scale refers to the level of observation or measurements that define the size and complexity of the geological structure. So, the scales in structural geology are typically characterized into three: microscale, mesoscale, and of course, microscale. So these scales are very important, mainly for um mainly for let me do this. So for the accurate interpretation, okay, and many other things. So in terms of accurate interpretation, for example, let's look at the microscale, okay, wherein we are looking at the hand specimen. So features like mineral orientations, the grain boundaries, and micro cracks can provide a valuable insights into the deformation mechanism and conditions. All right. So, but in terms of the mesoscale, outcrop patterns such as folds, and fractures are essential for understanding the broader structural framework and the history of that area. But when we're looking at macro scale, okay, a large scale, we are looking at large scale structures like, mountain belts, where two continental crust get to collide and form during an orogenic event, forming what you call the mountain belts. Rift zones and tectonic plate boundaries will inform about large-scale tectonic processes and the geodynamic environment. So just giving you, when we're looking at the accurate interpretation, looking at different scales from microscale and mesoscale, with a micro, we're looking at you're looking at the hand specimen, because you cannot be able to see that with your naked eye. So you're gonna see the mineral orientations, grain boundaries, and micro cracks, and this will tell you much about the deformational mechanism. So which is why scales is very important for a structural geologist. All right. So um So microscale refers to the smallest scale of observation, typically ranging from a few millimeters to a few centimeters, involves the study of individual minerals, rocks, and textures. Of course, using the microscopes, you can view that in thin sections, and then you'll be able to see the mineral orientations, the textures, and the minerals that are right inside that particular rock. So it's important for understanding the genesis or the formation and evolution of rocks, and as well as the formation of specific geological structures. For example, how can you understand the genesis and evolution of rocks? Let me give you example of using sorry about that let me give you example of what you call a pledge. Okay, a plagioclase. So if a plagioclase has got showing this, what you call this, spindle twinning, okay, so this will tell us much about the deformation. So if these plagioclases, they are showing or the spindle twinning, and then spindle deformation, and then we understand that that rock has underwent what you call the deformation. So it means that area must have underwent tectonic deformation. So which is why the microscale is also important. Okay, so Yes, you can now see we are looking at different minerals. Here we see plagioclase, here we see quartz, here we see the muscovite, and we are at the scale of 2 millimeters. You know, it's a smaller scale. You cannot be able, your eyes will not be able to see what's below this thin section. So you are using a thin section, and then using what you call the transmitted light microscopy, or the reflected light microscopy, and then you can understand the textures, the grain orientation, the grain boundaries, and many other properties that are seen within this rock. So this is what you call the microscale. So you are seeing what a normal eye cannot be able to see. So you are studying the growth patterns of minerals, examining the textures and composition of individual grains, and analyzing the fabric of rocks under a microscope. All right. And then mesoscale refers to the medium scale of observation, typically ranging from a few centimeters to a few meters, involves the study of large scale structures such as bedding planes, foliations, and lineations. All right. And then it's important for understanding the development and of large scale geological structures such as faults, and fractures. So you're gonna understand these large scale geological structures. So, if you see the faults, and then you understand that the area has underwent what you call a tectonic deformation, and then weakening the rocks, and then at the end, the rocks end up being broken, or they end up being fractured. But now, the faults, they tell you much about the compressional stresses, and then it means that usually you can see these things in convergent plate boundaries, all right, where two things they get to collide. So by looking at, when remember you said a structural geologist yeah, must also do what you call the field observation, beside using remote sensing, computer simulations, and many other things. You also have to do field observation. So if you see these folds, and fractures, then you understand that we are in the mesoscale, and then from that you're going to be seeing the fault planes, the hinges, and many other things. All right. But now, the mesoscale, for example, let's differentiate between a foliation and lineation. All right. So foliation, it's what usually seen in the rocks such as gneiss, because they have got what you call some gneissic bends. So those bends, they were because of the foliation, all right, due to the principal stress. And then you taking what was randomly distributed, the mineral grains that were randomly distributed, and then you are forcing them to orient themselves in the certain direction. And then by so doing, they end up forming what you call the foliation. But lineation, it just means the orientation of the rock features, right? Just means the orientation or the arrangement of the linear structures. Okay, so I hope you understand, but I'm going to show you in a few. Okay, so examples of mesoscales mapping include mapping the orientation of bedding planes and foliations, analyzing the geometry and spacing of folds and faults, examining the relationship between different rock units and their boundaries. All right, so let's check here. You see over here, you have the minerals that were randomly distributed, and then due to directed pressures, and then you force the minerals grains or the mineral grains to align themselves in a certain directions until they are in the form of foliations. Okay, they're in the form of bends. So this is what you see in the rock gneiss, right? And then if you can check here, we also have what you call the bedding planes. We've got the bedding planes. We've got the bedding planes. We've got the bedding planes over here. We've got the bedding planes, okay, the planes that are separating the beds, these are the bedding planes, these are the bedding planes, okay. So, and then you also have got now lineation, yeah, as we have mentioned that this is just the linear structures. So this is the schematic drawing. This is just example using what you call the drinking straws. If you pack themselves nicely in this order, and then this resemble what's happening in a hand specimen. So can you now see that this rock, it resembles what you call the lineation, the linear structural features in the deformed rock. Okay. So all these things can be observed using the mesoscale. I mean, your naked eye can be able to see the bedding planes, can be able to see the foliations, can be able to see lineations. You can see lineations over here. Okay, it's unlike the macroscale, wherein you need the help of the petrographic microscope. Here, you just have to be in the field and observe these medium scale features such as the lineations, foliations, and the beddings. And then by so understanding or seeing these features, you'll be understanding the tectonic history of that particular area. You'll understand the stress direction, the stress directions, and many other things. Okay. So microscales, on the other hand, refers to the larger scale of observation, typically ranging from meters to kilometers or even larger. I mean, it means for you to reconstruct, all right, you have to use different disciplines. You have to use different disciplines to understand. For example, if you're looking at mountain ranges, basins and plateaus, you cannot just observe them, let's say, at a single place or at one place, right? You have to check a wide range of area, right? So it's important for understanding the overall tectonic evolution and geological history of an area, all right? Which is why the macro scale is also important. All right. So mapping the distribution of different rock units and their relationships, examining the geometry and the orientation of large scale folds, and studying the relationship between different tectonic domains and their boundaries. All right. So if you can check here, you are looking at the large scale folds. You're looking at the large scale folds. You are looking at the large scale faults, so these rocks, this mountain, or this fault mountain, it's a typical example of a macro scale. Okay, so if you are looking at only at this particular area only here, you're gonna be at a mesoscale. But now check, you're looking at the entire area, the large area from few meters to few kilometers. Then that is example of large scale. And then this is the mountain building events, or the mountain belt, or the fold mountains. Here you also have during orogenic events, and then you can see you forming what you call mountain ranges. Mountain is a very huge thing, so the scale must be also larger. I mean, it's different than when you are here, when you are here, when you are here. When you are here, you're looking at macro mesoscale. You're not gonna see exactly what really, you're not gonna have a general idea of what really happened. But if you look at the entire thing at the macro scale, all right, you would get the general idea of what happened. So usually structural geologists, they start looking at the macro scale to get the general idea of what's happening, and then they go to the mesoscale, and then they go to what you call now the macro scale. Now when they are in the macro scale, they would be having a general idea of now what really happened. Then also the basins. Okay, it's the typical example of the macro scale. Okay, so moving right on. So we want to understand why the scale is very important to a structural geologist. It's important for identifying the patterns and the relationships, and then reconstructing the geological history, predicting or the geological behavior, and of course developing effective exploration strategies, exploring or developing the effective exploration strategies. For example, let's let's say you want to integrate the data. So if you're using what you call the data integration, so it means now you are by combining observations from different scales, right? From different scales, from macro or from micro to macro. So you are combining observation from different scales would allow a structural geologist to have a comprehensive understanding of the geological processes, right? Let me give you example. The microstructural analysis can inform a structural geologist about the conditions of deformation, while macro scale observation can contextualize these conditions within the regional tectonic settings. So you have to integrate the data. You have to combine all the data from the macro scale and to the from microscale to the macroscale. And then by so doing, you're gonna now be, when you're combining observation from all different scales, you'd have now the greater insight into the geological process that happened or that occurred within that particular area. So when you are developing the effective exploration strategies, let me give you an example. You can use some computer simulations. Okay, we can use computer simulations, for example. So now you are using what you call, you are predicting and you also model, right? So it means now if you understanding how, or by understanding how small scale features relate to large scale structures, would help in creating accurate geological models. Now these models are crucial for predicting the location for resources like minerals, oil, gas, as well as for the assessing of geohazards. So which is why we say developing effective exploration strategies. Okay. All right, because now you'll be understanding how the small scale features relate to the larger scale structures. All right, and then if you understand that relationship, you'll be able to create the effective models. All right, and then if you have now the effective models, these effective models will be able to help you predict where can you find mineral resources, oil, again, gases, and then now you can now start doing what you call the exploration. All right, now the other thing is, if you are recognizing features at different scales, you'd ensure or if you want to predict the geological behavior, right? Geological behavior, you'd want to understand the relationship between different geological structures and processes at different scales. All right, structural geologists can predict how rocks will behave under different conditions. All right, you'd want to predict how rocks would behave under different conditions. I mean, we've got rocks that are competent, we've got rocks that are incompetent. So for example, when you're forming the body nudge, so you need the rocks that are competent and those that are incompetent. So a structural geologist can predict how the rocks will behave under different conditions. Okay, and then you are reconstructing the geological history. All right, you are reconstructing geological history by studying the evolution of geological structures at different scales. The structural geologists can reconstruct the geological history of that particular area. So which is why these things or the scale in structural geology is very important. Okay. Sorry about that. Now, in the end, structural geology is it's very important, especially for what we call the problem solving in earth sciences. All right. So we know that many geological problems require multi-scale analysis to resolve. All right. For example, understanding the evolution of fault system may necessitate studying microscopic deformation features, individual fault segments, and the entire fault network. So it means we have to understand the relationship between microscale and meso and what you call the macroscale. So let's see each other in our third lecture, wherein we are going to be dealing with the isotropic and anisotropic rocks in structural geology. See you on the other side. Cheers.